This video is going to walk you through the top of page 3, which is number 6, an area problem that kind of incorporates some of the rules that we were discussing in the previous video that take into account the geometric interpretation of what's going on when you're finding an antiderivative and don't really have a function to worry about. In question number 6, letter A, the function f isn't given to us at all. And you could write a tremendously complicated piecewise function with 1, 2, 3, 4, 5, 6, 7 pieces, including a semicircle, but that sounds really tedious just to write that piecewise function, let alone have to do an actual antiderivative of each piece of the function, plug in the coordinates, subtract the coordinates. That just sounds like a lot of work. The beauty of knowing that an antiderivative is actually an area, and that an area is an antiderivative, vice versa, is that it gives us that flexibility to say, ooh, one of those options didn't sound so good, so why don't I try another one? Now, in letter A, we're definitely going to think about this in terms of area, and if you've started kind of noticing and digging a little bit deeper into the notation, you might have immediately kind of hit a mental stumbling block, because you might be going, wait. It says f of t dt, and then the original instructions say f of x, and the graph says f of x. What is going on? Is it a typo? Oh my god, they're all t's. What's happening? And I just want to point out to you, there is a reason for that. We have not yet discussed it. It has to do with the fundamental theorem of calculus, which is kind of scary sounding and very important, but it's a very abstract idea that right now has nothing to do with area. The long story short, which we'll get into in another video when we have a slightly more dedicated focus to just talk about notation, is that t is what we call a dummy variable, and the dummy variable ends up getting substituted out. We're not going to worry about that right now. We're just going to think about these in terms of area, and we're going to think of these as area problems, so don't let the letter t mess you up too much. Try to just appreciate that the most important part of this problem is the integral symbol itself with the start and the stop values, the 4 and the 4. That's telling us in code that I want to find the area from 4 to 4. And I'm going to write that out just so that way we can start to train our brain to think about those words when we see this symbol. I think that word association has kind of been a powerful theme that we've been building all year long, that I want to make sure we continue to build on, even as we're learning from home. Being able to have that word association constantly coursing through your mind is going to really help when you see an antiderivative with fancy symbols to give yourself something to latch onto and to say, oh, area, I can do that. Okay, 4 to 4, start, stop, got it. So let's think about this picture, and let's think about the area from 4 to 4. Those are x coordinates on the picture. So you can say x equals 4 and x equals 4. But most people, once they know that those are x coordinates, don't need to be that formal. Now, I took the liberty in my picture of actually labeling the x coordinates, which you might want to do just because it's kind of tedious to have to count them every time. But let's focus on that shape for a moment, and let's picture what's happening if I start at 4 and end at 4. Remember what we discussed in the previous video about that rule that kind of sounds familiar right now? If I'm starting at 4 and ending at 4, I have literally no base of any shape. I'll have a height. I can tell that there's going to be a -1 as a height at 4, but it doesn't even matter what the height is, because the base from 4 to 4 is going to be 0. 0 times -1 is going to be 0, so the area from 4 to 4 is virtually non-existent. It's not even a geometric shape, so the area is simply 0. Now you'll notice I'm thinking about it as an area, not as anything fancy, not as any calculus, so just keep those areas in mind. Because when you look at letter B, the area from 0 to 1, that should dictate your choices about how to visualize this shape. The area from 0 to 1 refers to the region in this little diagram that I'll highlight just so that way we can see it a bit more detailed. The area starting at 0 and ending at 1 must be that region that I just highlighted yellow. You might want to consider having some highlighters or some different colors to highlight and color code these regions in case it helps, but that's just an optional thing if you choose it. Now, the area from 0 to 1 refers to the area between the function itself and the x-axis. Whether it's above the x-axis or below the x-axis, we have to take into account. But right now, we're just thinking it's the literal area between the function and the x-axis, hence the yellow highlighted part here. Think about what I just highlighted. That is clearly a rectangular shape. Think about the area of that rectangle using your best geometric instincts. A rectangle's area is base times height. The base of this rectangle is positive because I'm starting at 0, ending at 1, so I'd be moving to the right. That width would be positive 1 to the right, times the height of this rectangle is clearly up from the x-axis, so a positive value, positive 2 units up to get to the top of the region. Means that it has a height of 2. Positive 1 for the base times positive 2 for the height is an area of 2. So I probably made it sound like it was a bit more complicated than it needed to be, but nevertheless, these are just area problems. That you are finding the area from the starting point to the stopping point of whatever's kind of trapped in between. So in question letter C, now it's asking us for the area from 1 to 3, starting at 1, ending at 3. Now this is where a little bit of organization might come in handy, because if you already know the area from 0 to 1, and then you need to kind of keep building additional areas, maybe using some different colors could help differentiate so that you don't get yourself too mixed up. Now let's visualize the area from 1 to 3. That would be this kind of triangle shape. So here I am going from 1 to 3, so that would be a positive base because I'd be moving 1, 2 to the right. It would be a positive height because I'd be going 1, 2 up. So that area would be base of 2 times height of 2 divided by 2, because that's the area formula for a triangle. And 2 times 2 divided by 2 is an area of 2. Now we're going to repeat that process every single step of the way. You can definitely tell in question letter D why being organized is going to come in handy. Because notice question letter D says find the area from 0 to 3. Now I'm looking back at my picture realizing I've already kind of highlighted the entire area from 0 to 3. So this might be a helpful time for me to recap that the area from 0 to 1, well that was already 2. The area from 1 to 3, I just calculated that as well. That's also 2. So if I want the entire region from 0 to 3, that would be this 2 plus this 2. No need to calculate it all over again. I already know that that's the sum of the areas. Remember our rule from the previous page? That's what we were talking about. To find one big region, you can always just add up 2 smaller ones. So the area from 1 to 3 must be 2 plus 2, or 4. And again, the beauty of this is that if you just approach it as a basic geometry problem, you're really doing all the fancy stuff that you need. No need for extra. Now, all of these questions are basically just going to ask you different area problems. They're going to ask you to focus on different parts of the shape. Some of the parts are obviously going to be a little bit more nuanced than others. So you might have to use combinations of triangles, rectangles, trapezoids. In this little region from 6 to 10, you're going to be doing the area of a semicircle. So just as a reminder, because that's probably the one formula that we don't really use very often, the area of a circle is radius squared times pi, or pi r squared. And the area of a semicircle, which is half of a circle, is pi r squared divided by 2. So if you want to make a little note to yourself just for the area formula, that would be a good thing to just make sure you know. In terms of AP, they typically do throw semicircles in there, sometimes even quarter circles where you'd be dividing by 4. So just familiarizing yourself with that formula is a good idea. Obviously this year we're not going to have to memorize formulas because it's theoretically open note, sort of officially, unofficially, wink wink. So maybe record a formula sheet somewhere of basic areas in case you need a quick little reference tool. Now by the time you get through some of these, they're going to get a little bit more challenging. So here's the goal. I'm going to suggest that you try as many of them as possible from A through V just by using your geometry skills alone. Some of them will be a little bit more challenging, and that's okay. So what I expect you to try is anything that you think is relatively straightforward, anything that you think kind of looks doable with basic geometry skills. And leave blank anything that you're like, don't know about that one. But look at the answer key. Maybe reverse engineering it would help. That if you look at the answer key and say to yourself, okay, if that's the answer, where'd that come from? Where would she have gotten that number? Why does that make sense? And see if working backwards can help. I think there's a lot of merit to starting with an answer and reverse engineering the process, because sometimes you learn a lot more that way, just by thinking through the steps in reverse. In any case, the only ones that I foresee becoming potentially problematic are letters R, T, and U, because they have the absolute values. So in the next video, I'll discuss those specifically. Otherwise, I'm going to expect that most of these can be done with basic geometry skills. Just pay close attention. The only ones that I can, again, foresee being tricky are things where you just have to think a little bit and you're not just blindly calculating. Letter F might be a great example of such a thing. Letter F is the area from 6 to 3. And I'm purposely writing this so that way you can think about this as you're doing these problems with that order of an integral in mind. The way this is written is the area from 6 to 3. Remember, the bottom is always the start and the top is always the end. It doesn't matter if the start's bigger than the bottom or the top. It's the locations of the numbers that dictate start and stop, not the size of the numbers. So this is saying on my picture that I want the area of the region starting at 6, ending at 3. Think about how that would look for a second. If I started at 6 and went towards 3, that would definitely be a negative base, because 6 towards 3 is going to the left. Now, if I think logically, that would be a distance of 1, 2, 3. Negative 3 for the base. Now, since this is a triangle, I want to keep in mind my formula, base times height divided by 2. So I need the height of this triangle. Now, this triangle is underneath the x-axis, so its height is also negative, because to get to the height, we'd go down. So the height would be to the edge of the triangle here, -1 unit. And since the area formula for a triangle is base times height divided by 2, I would have -3 for my base, because we're going backwards, times -1 for my height, because I'm going down, divided by 2 would be positive 1.5, or positive 3/2 if you want to think of it that way. So that area, weirdly enough, does come out to be positive. And that's why you don't want to make too many assumptions about these problems. If you see something like letter F and your brain's immediately like, ooh, it's backwards, it's going to be a negative answer, be careful. This involves just a little bit of, sorry, not coronavirus, I promise, just a little bit of thinking, because we have to pay attention to the directions of both the base and the height. That's the thing that you just have to kind of be careful about. Use the answer key, use your best common sense when it comes to just straight up geometry, and see how many of these you can do. In the next video, we'll discuss the specifics with the absolute value, and then hopefully you'll be well equipped to do more problems like this in the next lesson.